All right, so have a nice day, everyone, once again. So this is another video for the graph, data structures and algorithm, the same thing. So we will continue with the graph adjacency matrix. So in this video, we will be going to tackle this kind of adjacency matrix then. Since in the previous video, I was able to discuss the types of graph as well as the representation of the graph. So just um, watch that video in order for you to understand the basic of graph. So let's actually proceed with the adjacency matrix. So when we say adjacency matrix, that is a square matrix used to represent a finite graph. So when we say matrix, naka-square na sa, diba? When we define matrix, that is something like that. So if what will be your node, that will be implemented in a column and in a row. So say for example, talan mga node is E, A, B, and C, D, E. So dapat it must be there as well. So you have to define that as well so that you can also find the what they call this one? The adjacency of the matrix and so on and the like. Now that indicates whether pairs of vertices in the graph are adjacent and can be applied for both directed as well as the undirected graph. So it must be symmetric for the undirected. Just take note for the undirected graph, something like this, it must be symmetric. So we can actually define what is symmetric data structure. Symmetric in the future. So we will be going to check that later on. So for directed graph, that is also not symmetric since it will be different. It will be different structures. So um, let's try to continue. 1 second. Okay. So here then, adjacency matrix let the graph equals to the vertex as well as the edge be a graph with the n vertices. So the adjacency of matrix of G of your graph is a two-dimensional. So naka two-dimensional as what I mentioned. All of your um, rows must be defined as well as your columns must be defined. What will be your node contain what has your node, you must also be declared that here at the rows and columns. So two-dimensional n by n array, which denoted as adjacency matrix. So here, how can we know that they are adjacent? How can we define? So by interpreting this one, if the edge of VI, let VI and VJ. Say, for example, this will be your vertex I, and this will be your vertex J. You compare that, each vertex, if they don't have a relationship. If your graph, if the edge of that graph, if it is equals to the adjacency matrix, or I and J, if that consists, if that is actually present right there, that is containing in that kind of certain matrix or edge that is equals to the graph. In the vertices. If that vertex do have a edge or they do have a relationship with each other, that means to say you have to print as one. It will return as one. So if A to B, so say for example, it must be 1 here. So let's try to check that later on. So if there is no edge in your edge and that graph, that node, so therefore your adjacency matrix I and J, say for example C and B, they don't have any relationship. So that must be equals to 0. So that's how it works here. Now, The next one will be the this one. Let's try to identify the adjacency of that. So let's try to check how to identify. So as what I've mentioned, that in your adjacency matrix that is n by n. So let's try to uh, define first the what are the rows in the column of your matrix. So you have here letter A, letter B, letter C, D, as well as E, diba? We also have here letter A, in your row, you have C, D, and E. So in your matrix, you have to compare the each address. So A and A, is there any A to A? Is there any loop? But there's nothing. So that is 0. That is equals to 0. So if you will check that everything B to B, C to C, D to D, and E to E, there is no relationship. So we can identify that B to B, 0, C to C, 0, and D to D, 0, E to E is also 0. So can now easily says that you since there's no loop, so tanan all of your all of your things that denotes to itself supposed, since there will be no directions for that, so therefore that is equals to 0. So now let's try to define A to B. Is there A to B? There is A to B relationship, and that is 1. And A to C, A to C. So in your A to C, there is a relationship that is 1. So A to D, A to D, that is also 1. A to E, A, then E is not connected, so that is 0. So remember that we are doing a undirected graph. So in your undirected graph, means to say you can definitely um, work that, or you can identify that both as A to B or B to A. You can read that vice versa, diba? So that's how it works here in your adjacency matrix pertaining to the undirected graph. Now, so that it will be easier, since you can read that vice versa, B to A, D to A, and C to A. So you can definitely say here B to A, 1, C to A, 1, D to A, 1, and E to A is 0. So somewhat ano lang, similar to this here, but it's in your row A here. Now, let's try to identify for the B right now. BA and BB is already identified. Let's proceed with the BC. Is there any path from B to C? But there's none, so that is 0. B to D, there is a relationship that is 1. And B to E, there is a path that is equals to 1. So since we can read that vice versa, so we can definitely put that here. We can just copy 0, 1, 1, 0, since CB is not connected. So DB is connected and EB is connected. So that is correct. Now, um, how about for the C, um, node C? You will identify that as well. So since we identify the CA, CB, and CC, let's try to check for the CD. CD, there is a path, so that is 1. And CE, there is no path, so that is equals to 0. Since we can also do that in vice versa, since there's no direction in that manner, so you just can copy that one for DC and EC. Ba? Now, since we already identified the letter C, so we will go to the D right now. So for DA, DB is already identified there, the DC, as well as the DD, and for DE, let's try to check. Is DA is connected to each other? Yes, they are. So that is equals to 1. Equals to 1 here for ED as well, since you can check that in vice versa or read that vice versa. So right now we already checked by the D. For E, we have here the EA, EB, EC, ED, and EE. We already do have that. So it means that this one will be your adjacency matrix. That is how you will do, or you will create the adjacency matrix, and that's how it works here. So to identify everything, so this will be how it works. So for the adjacency matrix to clarify, that will be how the adjacency matrix work then. So if you do have any questions with that one, you can just ask me anytime. So since as what I mentioned earlier, that the undirected graph must be symmetric. When we say symmetric, let's try to define what does it mean. So symmetric means if you will transpose the rows into column, it must be the same as is, the same formation. So in your first row, A, you want to form that in a column, for example. So 0, 1, 1, 1, 0. Next, 1, 0, 1, 0, 0, 1, 1. Next is 1, 0, 0, 1, 0. Next is 1, 1, 1, 1, 0, 1. And 0, 1 for this one here. 0, 1, 0. So that's how you will do that. So if you will check that right here in your adjacency matrix result. So by comparing that, we already transposed that here already. So they are still the same formation. There's no changes. 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0. So by um, transposing the rows into column, it will still print the same. That is symmetric all about. So if not symmetric, does not equal to itself when you will transpose the rows into column. So let's try to check that the next one. Okay, for adjacency matrix for the directed graph. So for directed graph, it will be different manner, since you do have a outgoing order or outgoing arrows. You will just only count the outgoing arrows, not the ingoing. So you will check that here step by step. So you have to compare each adjacency grid. Will not, since you cannot control, or you cannot interpret that as, what you call this one, you cannot say that that you can read that as vice versa. No, here you can't read that in vice versa. Now, here then, let's try to check that one by one. Then let's try to identify the adjacency matrix pertaining to the directed matrix right now. Okay, so sorry. So A to A. since wala loop, so there's no loop, we just put 0 A to A, B to B, C to C, D to D, and E to E, since there's no loop in our structure right now. So that means to say um, it is 0 already, automatic. Now, for the next one, for the next thing, we will also definitely check right there the next figure here for the A to B. Is there any outgoing for A to B? So outgoing ang basihan mo, ha? It will not matter with the ingoing. So the from A, is there any outgoing to B? So there is a relationship from A to B. So A to B is adjacent. But for B to A, there B to A, that is not accepted. So that is 0. Diba? And for A to C right now, is there any outgoing? So yeah, there is, and that is 1. How about for A to D? There is no path from A to D, so that is 0. How about for A to E? So there is no path, that is 0. Let's proceed with the B. BA, there is a arrow, but it's not pointing to A. It's not B to A. It is specific to A to B, so that is 0. For B to B, there's no loop. For B to C, B to C, there is no connection, so that is 0. How about for B to D? Yeah, that there is, so that must be 1. And how about for B to E? Yes, it is existing, that is 1. How about for C to A? C to A is not connected since it's ingoing to C, so that is 0. So how about C to B? There is no direct path, 0. C to C, there is no loop. C to D, C to D is connected, so that is 1. How about for C to E? They are not connected, so 0. How about for D to A? D to A, there's no connection or edge there, that is 0. And how about for D to B? There is no connection, still the same thing, so that is 0. D to C, there is no connection that points to C, 0. And how about for D to E? So there is a connection, so that is equals to 1. How about for E to A? E to A, there is no direct path, that is 0. How about for E to B? There is no direct path that from E to B, so that is 0. E to C, there is no direction, that is 0 still. And for E to D, that is not connected from E to D, so that is 0. And E to E, no loop, that is 0. So this is your result right now for the adjacency matrix for the directed path. So to clarify, so this will be the adjacency matrix for the directed graph. So it is basically so easy. So be mindful that you have to search that one by one. So since as what I mentioned earlier that the adjacency matrix of directed matrix will not be symmetric. So we will try to transpose that. 0, 1, 1, 0. Then 0, 0, 0, 0, 0, 1, 1, and 0, 0, 0, 1, 0. Then 0, 0, 0, 0, and 1. Then all 0. So let's try to figure out if that's still symmetric. So try to check all zero, but here it's not. So that means to say it is not symmetric anymore. For the second one, zero, zero, so it's 1, 0 here, so that's not symmetric. So that's how it works in directed matrix. So it is not symmetric anymore. So that's actually how adjacency matrix will work. So that is basic, and hopefully you understand what how does adjacency matrix work. So if you have any questions pertaining to that, you can just message me through MS Team, and in the next video, I will also illustrate how to do with the adjacency of list then. So thank you so much.